So the last of our major conservation laws that we need to set up is the conservation of angular momentum. And so to preview that, what we're going to do is we're going to step back to talk about conservation of linear momentum, because as you'll see, where conservation of momentum comes from is very similar whether you're talking about linear momentum or angular momentum. So with linear momentum, it all starts from thinking about the translational version of Newton's second law, and in this case what we want to say is that the net force acting on our system is equal to the time rate of change of the linear momentum of our system. So this is where we've added up all the linear momentum vectors from any object that's part of our system, and we want to think about how that changes with respect to time. That has to be equal to the net force acting on the system. I divide the dt over. I can break up the net force into thinking about internal forces and external forces. Because of Newton's third law, I know that the internal forces, when I sum them up over my entire system, those will cancel out, and so I'm left with the net external force acting on the system. I can integrate this equation, and so if I integrate the left-hand side from some initial to final momentum and the right-hand side from some initial to final time, what I get is that the change in the linear momentum of my system is equal to this integral of the net external force with respect to time. All I'm going to do at this point is make two slight changes in notation. One is I'm going to break up this delta p term, and so this is final minus initial linear momentum, and then I'm going to take the initial linear momentum over to the same side of the equation as the integral. That gives me the total initial linear momentum of my system plus this integral is equal to the total final linear momentum of my system. And then the second notational change I'm going to make, what do I mean when I talk about the linear momentum of the system? It's just the net linear momentum. Add up all the linear momentum vectors initially, add up all the linear momentum vectors at the end. So what we have here is an equation that should look pretty similar. It's a lot like what we've called our energy balance equation. It's just that in this case it's keeping track of the linear momentum of our system. So we can think of it as a linear momentum balance equation, because what it tells us is the total initial linear momentum of your system plus this integral of the net external force acting on your system with respect to time is equal to the final linear momentum of your system. What this equation fundamentally is telling us is how the net external force acts on the system over some period of time changes the linear momentum of your system. So what are the important details we need to remember when working with this equation? Well, the first is this equation tells us explicitly what causes the linear momentum of a system to change, and it's this integral, right? This integral we've given a name before, right? We said this was the net external impulse acting on the system, and the net external impulse is what changes your system's momentum. This equation also tells us when the linear momentum of your system is conserved. So again, if this integral is zero, then what that means is that the total initial linear momentum of your system is equal to the total final linear momentum of your system. So when is it that this external impulse is going to be zero? Well, there's sort of two conditions. The first is if the net external force is zero. The second is if you consider really brief periods of time. So even in situations where you might have a net external force, if the time over which you let that force act is really, really small, in almost any of those cases, you can still treat the net external impulse as if it's zero. The third thing is that this is a vector equation. And of course that means what we expect it to mean at this point in the course, which is there's a component equation for each relevant dimension we have in our problem. So if we have a one-dimensional problem where the linear momentum of our system is all in the x direction, we only need one equation. If we have a one-dimensional problem where the linear momentum of our system is all in y, we only have a single equation. If we have linear momentum of our system in both the x and y directions, then of course we need two equations. If we think about this x equation, again, when is it that the x component of the linear momentum is conserved? Well, that happens when the x component of the net external impulse is zero. So our integral here is also part of this component equation. And so if the x component of the net external impulse is 0, the x component of the linear momentum of your system is conserved. The same is true for the y component. So if the y component of the net external impulse acting on your system is 0, then the y component of your total linear momentum is conserved. So our conservation of linear momentum simply came out of thinking about the translational version of Newton's second law. The conservation of angular momentum is similarly come from thinking about the rotational version of Newton's second law. So now that we have objects that are extended objects, the rotational version of Newton's second law tells us that the net torque acting on our system is equal to the time rate of change of the total angular momentum of the system. I can take the dt over to the same side as the net torque. The net torque, I can break that up into internal torques and external torques. And again, the internal torques, that's just torques that one part of my system generates on another, and when I sum them over the whole system, they cancel out. And so I'm left with the net external torque acting on the system times my differential time element dt has got to tell me about how the total angular momentum of my system is going to change. I can integrate this equation on both sides. So again, integrate from some initial to final angular momentum on the left side, from some initial to final time on the right. And what I get is that the change in the angular momentum of my system is equal to this integral with respect to time of the net external torque acting on the system. Just like with our linear momentum equation, we're going to undo the delta L term. So this will be final minus initial, take the initial over to the other side. I get this expression, and then again, we're just going to notationally change from writing this as the angular momentum of the system to putting that sigma sign in there, which again is just emphasizing that this is add up all the initial angular momentum vectors for your system, add up all the final angular momentum vectors for your system. So that calculating the initial and final angular momentum of your system is just a vector addition problem. So what we've got here is an angular momentum balance equation, and what it's telling us is how the net external torque acts on our system over a period of time is going to act to change the angular momentum of the system. So what are the important details when working with this equation? Well, most of these are very similar. So again, we're going to start by saying that this equation explicitly tells us what causes the angular momentum of a system to change, and it's this integral. Right? So this integral we can think of as the external angular impulse. So this is the net external angular impulse acting on our system. A net external angular impulse acting on your system will cause the angular momentum of your system to change. If the net external angular impulse acting on your system is 0, then the angular momentum of your system is going to be conserved. So again, if this integral goes away, then that tells you that the total initial angular momentum of your system is equal to the total final angular momentum of your system. So under what conditions is this integral 0? Well, two options. Again, one of them is that the net external torque acting on your system is 0. The other is if the time interval you allow that net external torque to act is effectively 0, then there's no time for that external torque to generate an external impulse. So with linear momentum, this was the argument we often made for why we could still use conservation of linear momentum when collisions occurred. We're going to be able to make the same argument here, that when things collide, whatever net external torques there are acting on the system are going to be smaller than the internal torques that the pieces generate on each other as they collide, and the time the collision occurs is going to be small enough that we can treat the external angular impulse as 0. 3. Again, this is a vector equation. So just like with linear momentum, our angular momentum balance equation is a vector equation. The nice thing is that again, we're going to focus on forces that act in the xy plane, which will generate torques about the z-axis. So it is a vector equation. It's simply a vector equation that for us, we're going to focus on a single direction. So of course, when the net external torque its z component is 0, then we're going to be able to say that the angular momentum of our system about the z-axis is conserved. The one additional detail that applies to this equation that we didn't have to worry about with linear momentum was that, of course, this equation is dependent on your choice of pivot. So to be more explicit about what this equation says, it's telling us that the initial total angular momentum of your system about point O plus the external angular impulse exerted on your system about point O is equal to the final angular momentum of your system about point O. So one of the things that we need to keep in mind is that there may be times where whether or not the angular momentum is conserved can be a function of our choice of point O. So where we choose to put the pivot, there may be situations where, depending on the point you pick, this integral for the net external angular impulse might disappear or it might not, depending on your choice of pivot. So all the fundamental pieces that describe conservation of angular momentum are now sitting in this equation. And so what we'll see in the next video is, now that we have some sense of why angular momentum is conserved and under what conditions angular momentum is conserved, how do we work problems when angular momentum is conserved?